So in the next section, we will talk about the mechanical forms of work. Well, as mentioned before, work is the energy transfer when the force is exerted on the object through a distance. And here I use a W equal to Fs, same meaning as W equal to Fx, because S is a displacement, okay? Just the same thing, okay? Okay, more precisely, the work done is a dot product of the force vector and the displacement vector. We can write it to be W equal to F vector dot S vector. Okay, but the definition, there are two requirements so that there is a work transfer. First of all, there should be a net force acting on the system boundary, okay, so that this term would not be zero, okay? And another thing is that the boundary must move, okay, so that there will be some, you may say, deformation about the system boundary so that you will have work in this case. The expansion of gas into a vacuum involves no work, okay? Because there is no force acting on the gas during expansion, or we call this kind of expansion free expansion, because this kind of expansion is not initiated by any factor, okay? It's just expand freely, okay? It's not like heating a gas inside a piston cylinder device, okay? We need to input some energy so that the gas will be heated up. But in this case of free expansion, we don't need to have any input in this case, okay? Well, some common mechanical forms of work are discussed here. The first one is called the shaft work, okay? The shaft work is derived as follows, okay? First of all, suppose we have a force F here, and then we will have a torque in this case. The torque will be equal to F times R, okay? That should be the distance between the pivot and the side of this plate, okay? And here, N dot is what we call the number of revolution in this case. So how can we derive the shaft work? The shaft work is defined as W dot, the power, is equal to F times V, okay? So this V is the velocity times the force, okay? Because we know that velocity is derivative of the displacement. And here the force is constant. So when we differentiate the work done, the force term can be factored out. So we have F times V. And F, as I mentioned, it will be equal to what? Because torque, T equal to Fr, so it will become T divided by R. And V, using what we have learned in elementary mechanics, this V is called R omega. R omega. Okay, omega is the angular velocity, and we will later modify this term, so it will be equal to T omega. Okay? But this omega can be converted as what? This N dot is what we call the number of revolution per unit time, okay? We can write this omega as a displacement over a certain period of time so that it becomes T times 2 pi times N dot. So that would be the number of revolutions. So here, omega is the angular displacement per unit time, and we just convert it to be 2 pi N dot. And here we have derived this expression that will be 2 pi N dot times T. Originally, this term is in power, so it will be watt, but we usually convert it to be kilowatt, okay? Okay, another one is the spring work, okay? That's the work done on the spring when the force is applied to compress or extend the spring. Well, by Hooke's law, the force F exerted on a linear elastic spring is given by F equal to Kx. That will be Hooke's law. So Hooke's law is F equal to, originally it should be negative Kx, but here we just concerned about the magnitude, so it will be K times X. Okay? Originally, we need to include a minus sign, okay? But here I just neglect that, okay? Well, the work done will be determined by integration because we know that when you compress or extend the spring, when there's a change in X, the force also changes. So we need to use integration. So W will be equal to integration, suppose from position 1 to position 2, okay? F dx. Okay, and then it will be equal to from 1 to 2 kx dx. Okay, kx dx. And by the rules you have learned in integration, then you will have 1 over 2k times x2 squared minus x1 squared. So we have the expression for spring work. Okay. Other common types of mechanical work include work done on elastic solid bars as well as surface tension work. Okay? Well, elastic solid bars behave like a linear elastic spring. Well, as long as the force is not large enough to cause permanent deformation, or we call that to be the plastic deformation. If the force is large enough, then some of the bonds may be broken and bonds would be formed when the molecules move into a new position. Okay, so we will have this kind of permanent deformation. Okay, for more details, please refer to solid mechanics. Okay, if the force is not large enough, we can use the similar method for linear elastic spring to find out the expression about the work. Okay, so we can use the same method for obtaining the spring work to obtain the work done on the elastic solid bars. Alternatively, we can also use normal stress, that is the counterpart of pressure in solids, to obtain the work done. It is given by this expression, that is elastic work equal to from 1 to 2 F dx, that would be equal to from 1 to 2 sigma n A dx. Sigma is the normal stress, as I have defined before. This is the force per unit area, so force equal to sigma n times A. This A dx is actually a very small increment of volume. Okay, so sometimes it will be grouped into d times v. Okay, but here we haven't do any further simplification. Okay. Okay, another thing is surface tension work. Okay, we know that at the surface of a liquid, the liquid molecule will form an elastic film so that they would not be pulled towards the inner part of a liquid by the intermolecular force. Okay. The molecules at the surface, they will be attracted by the intermolecular force at the interior of the liquid, okay? But it will be repelled by the high density of molecules at the interior, okay? That means the interior of this liquid originally contained many molecules. The molecules at the surface cannot get into it. So the surface would become an elastic film, and there will be surface tension. And this kind of force per unit length will be called the surface tension, okay? So let's see this figure. If we would like to stretch the liquid film with negligible acceleration, an external force needs to be applied because there would be surface tension force pulling you against the expansion. And the work done will be given by W surface equal to from 1 to 2 sigma s dA in the units of kilojoule. Okay? So after you have calculated this integral, you just convert the units from joule to kilojoule by dividing the term by 1000. Okay? And the sigma s will be the surface tension. So W surface will be the surface tension work. And here, dA should be equal to 2b dx. 2b dx. Here, the dA here should be equal to 2b dx. Okay? Why 2b dx? Because in this liquid film, there will be two surfaces exposed to air. So 2b dx. Okay? But during a simple force balance, because there is negligible acceleration, then we will have F equal to 2b sigma s. Okay? So we will have a force balance here. Okay? As I've mentioned, we have negligible acceleration in this case, so it will have F equal to 2 sigma s times b. Okay? B is the length in this case. So when we multiply sigma s by b, then we will have this expression. Because we have two surfaces, there will be 2 sigma s in this case. Okay? Another important class of mechanical work is of the following. Okay? If work is done to raise a body with no change in velocity, it is equal to the increase in the potential energy, and vice versa. Okay? If work is done to accelerate a body, it is equal to the increase in the kinetic energy, and vice versa. Okay? The latter type of work done is given by the work energy theorem that you have learned in elementary mechanics. Okay? You should have learned this in Physics 112. Okay? If not, then please consult a elementary university physics textbook. Okay? It simply states that the net work done on an object will be equal to the change in kinetic energy. This theorem relates the energy transfer as well as the change in the energy stored inside the system. Okay? These two types of work done are more common than the work done on the elastic solid bar as well as the surface tension work. Okay? And they are useful in some of the common devices such as the turbine as well as the escalator. Okay? Well, there are also non-mechanical forms of work besides the electrical work. However, only electrical work is more common in the study of thermodynamics. So please read the textbook for other kinds of work if you are interested in that.